It's time. All right, welcome to lecture 2. I'm going to start with a little bit of a recap of what we talked about last time, but the ultimate goal of today's lecture will be to explain this thing right here, black hole radiation. Okay, so we ended last lecture by discussing, there were two things that we discussed. First is that rotating and charged black hole obeys the first law. And the first law looks like this. So I'll write T ds equals dm minus phi dq minus omega dj. And we identified this temperature with the size of the black hole. So the temperature we wrote down last time was R plus minus R minus divided by 4 pi R plus squared plus A squared. Okay? So all we did to derive this formula was we looked at the black hole solution and we assumed that we had a first law. So we assumed that we could write the entropy as A over 4G. And then we took a variation of the entropy and wrote it in terms of the parameters of our black hole. So for the mass, the charge, and the angular momentum. And the relation has a proportionality constant in front of ds, and we identified that with the temperature. Anybody remembers that from last time? So, so just assuming this relation, so we argued that the entropy should be A over 4G. Assuming this, well, we argued that it should be proportional to the area. We haven't derived that the proportionality constant should be 4G, 1 over 4G. But say I gave you that that is the proportionality constant, then you can look and see if I write down the variation of the entropy with respect to all of the free parameters of the solution, the mass, the charge, and the angular momentum, then this object that I write down looks very much like a first law, where the temperature is this object, which we argued for in a different context. So I'm going to remind you of that again. And I'm going to do the example of the Schwarzschild black hole so that we don't have to deal with all of the complications of a charged and rotating black hole. So remember, I wrote down the Schwarzschild metric. So that's the Lorentzian Schwarzschild metric. Remember, we then went to Euclidean signature by analytically continuing the time variable, and we found that in order for the geometry to be smooth, so in order for the geometry to not have a singularity, a conical singularity at r is equal to 2n is equal to r plus, then the Euclidean time coordinate had to be compact and identified with an inverse temperature, tau plus beta, where beta was equal to 1 over 4 pi r plus. You guys remember this? So, the reason that we have a natural inkling to associate this with a temperature comes from the fact that when I look at the Euclidean path integral and I identify the Euclidean time coordinate, then naturally I'm computing a trace, and the trace is something that I compute in a thermal ensemble. So the surprise that you might find is that if I look at the first law, I get this temperature, and it matches this expectation from thermal quantum field theory when I identify the Euclidean time coordinate. Now, a priori, these two definitions of the temperature are not related. And today, we're going to relate them. That's the goal of today. So understanding why this temperature that you get from the Euclidean method and this temperature that you get from just varying the parameters of the black hole give you the same answer. And it's a remarkable thing that these two things give you the same answer, but you will see and you will compute today with your own two hands why they're the same. Okay? Is that clear? All right. So one last thing I want to mention before we delve into how we relate these two quantities is I want to mention something that should make you uneasy before we even start to talk about all this equilibrium stuff. Okay? How's the video looking? Is it everything good? Everything easy to see? Okay, so the thing that maybe should make you uneasy is the following. Remember that I wrote for you well, you guys know this relation, that R plus is equal to 2m, right? This is the location of the Schwarzschild event horizon. And the temperature of the black hole, sorry, this is the temperature. So T was 1 over 4 pi r plus, and beta, which is a length, is 4 pi r plus. So I apologize for that. Okay, so m is related to r plus in this way, and the temperature is related to r plus. So we have m is r plus over 2, and temperature is 1 over 4 pi r plus. And now I'm going to give you a very quick exercise to see if you're awake on a Monday morning. And the exercise is compute dm dt, or also known as the change in the energy as you change the temperature. So, and remember, this is a collaborative class, so if you don't know your neighbor, introduce yourself and start discussing. Very good. Minus 1 over 8 pi t squared. So why should you be surprised by this result? The heat capacity is negative. Very good. Yeah, but okay, we're talking about equilibrium thermodynamics. Equilibrium thermodynamics assumes equilibrium. Equilibrium objects are objects that are in thermal equilibrium. And negative heat capacity tells you that if you try to increase the temperature, it will want to spew out energy rather than increase in energy. That's not something that is expected for a system in thermodynamic equilibrium. And this is the first piece of evidence, if you trust these relationships so far, that a black hole is not a stable object. This is the fundamental reason why black holes evaporate. We'll talk about the evaporation in a bit. But this notion that a black hole wants to get rid of its mass is because it's not in thermal equilibrium, and it is an object with negative specific heat. Its heat capacity is negative. That's why it wants to spew out its mass. Holds for charges in rotating black holes. It holds for, not quite. So there are limits where you can get the specific heat to be positive, but that requires you to be able to tune the temperature to be arbitrarily low. There are limits. Very near extremality, black holes get a positive specific heat, and that's because very near extremality they develop a very long throat. The proper time it takes for you to fall into the black hole gets very large, and so the thermal radiation actually gets trapped in this well and falls back in, and so the black hole can't really spew out all of its. Is this the same as the gene's instability? I don't think this is the same as the gene's instability. No. I think this gene's instability is different. But I'm not sure. The gene's instability is a classical thermodynamics. Yeah, so I think this is a different instability. But I don't want to like say definitively that I think that they're different, but my guess is that they're different. Okay, so the goal now. Okay, now. Also, I'll mention another thing that should be a bit surprising, is that for a solar mass black hole, if you try to compute the evaporation time using some very crude approximations, you would get that the evaporation time for one solar mass is 10 to the 66 years. 10 to the 66 years is much, much larger than the age of our universe, which is 13.6 times 10 to the 9 years. So roughly 10 to the 10 years. So the evaporation time for a solar mass black hole is very far out of the realm of effective field theory. So you have to take a lot of what we say with a grain of salt, because who knows what the laws of physics will be in 10 to the 66 years. Okay, so this really brings us in a very bizarre realm where you can do these calculations, you find that the black hole wants to evaporate, but the black hole will evaporate in a time that's so large that maybe you might consider that we should just completely ignore this effect. It's not within the realm of like the physics of our universe. We'll never observe it. It's kind of silly to even think about it. And nevertheless, hopefully by the end of this course, you will see that you can, even with this fact, make a sharp statement about why effective field theory in a black hole background leads to very, very dire problems. Okay. All right. So that was the introduction. So now we're going to get into the meat of today's lecture. Where did I put the eraser? Okay, so all of the things that we discussed so far, we had to make the assumption that the proportionality constant between the area and the entropy is 1 over 4g, And now I'm going to try to make an argument for you of why that proportionality constant is what it is. And in order to do that, I'm going to work in the framework of quantum field theory. So is everybody here confident that they can do quantum field theory calculations? Yeah? Roughly? Shouldn't be too hard. It shouldn't be too hard. We're going to take it slow. And we're going to work in free quantum field theory, which is hopefully the easiest. But you'll see, we can derive some cool stuff. All right, and to make our lives even simpler, we're going to work in 1 + 1 dimensions. Okay, so the setting right now, 1 + 1 dimensions, flat space, and we're going to work with a massless free scalar field. Okay, so that means that I have a metric tensor, which is 2 by 2 matrix, diagonal, 1 negative, 1 positive eigenvalue. And I'm going to work with the following scalar action. So far, so good, right? Everybody's okay with this? And I'm going to put a 1/2 and a minus sign in front because the kinetic energy has to be positive. Okay, so let's derive the equations of motion. What are my equations of motion? I want more explicit than square. How about in terms of dt's and dx's? Very good. Okay, so we have a very simple PDE, and we want to solve it. What is the most general solution? Very good. So the most general solution, I'm going to write it in terms of a basis. And the basis is they're plane waves. And I'm going to be very explicit with my 4 pi's and my so on and so forth. So the most general solution, which I'm going to call phi m, function of t and x, is the integral from 0 to infinity of dk 1 over root 4 pi k, some coefficient ak, e to the I k times x minus t, plus, I'm going to call this ak plus e to the minus I k x minus t, and then plus t to minus t, and ak goes to a minus k. That's why I did the integral just from 0 to infinity. So these are what we call right moving as t increases x increases to keep the plane wave centered. So these are right moving. And if I take t to minus t, then these are left moving. Okay? And this is the most general solution. Why is this the most general solution? Well, if you think I went too fast, it's very simple. If I take phi is proportional to e to the I omega t plus ikx, and I plug it into this equation, then in the equation of motion, 2 time derivatives gives what? Minus omega squared plus, because there's a minus. And 2 space derivatives gives minus k squared times e to the I omega t plus ikx. So to solve the equation of motion, this implies that omega is equal to plus or minus k. So that is why we have these expressions. Most general solution. Okay? If I want to set the values for A and A dagger, and A minus and A minus dagger or plus, then I need to specify an initial condition or a boundary condition. So far we haven't used any of the freedom, or well, we have too much freedom. We have to set an initial conditions in order to specify what these A's and A daggers are. Is that okay?
Do we assume this scalar field is real?
We assume it's real. I mean, the action is real, but it has one component. So the solutions are complex, but that's okay. There's a 1 degree of freedom.
And no 0 mode. And no 0 mode.
Yeah, we're taking the integral down to 0, but their 0 mode is hard to deal with. But I'm not going to discuss that. The 0 mode is annoying if you want to compute the path integral. Okay. So, how do I quantize a system like this? What is the first step that we do in canonical quantization? Can anybody tell me? Very good. All of those answers are correct. So, canonical quantization involves imposing that the canonical momentum and the field pi of x, phi of x, obey the Schrodinger or the Heisenberg algebra. So this should be a y, and then this should be an I delta x minus y. And pi is the canonical momentum, so in terms of the original field variable, pi would be phi dot. But in order to impose this, then you would find that this leads to ak and ak dagger become operators. And they obey exactly the raising and lowering algebra that you might have seen when you studied the simple harmonic oscillator in quantum mechanics. So that algebra is the following. And Okay? Is this familiar? Am I saying stuff that's new to people? If it's familiar, shake your head very vigorously so that I can. Okay, very good. So, uh, so this is the harmonic oscillator algebra, and one thing that I want to remind you of before we move on is that we have a Hilbert space. So this gives us a natural notion of a Hilbert space, and the Hilbert space is a Fock space. So we build it by acting with these A daggers, which are like the analog of our raising operators in the simple harmonic oscillator. So that is to say that there is a notion of a ground state where there's no excitations, and then we start exciting by acting with A dagger. So the ground state, where's the right place to write it? The ground state, I'm going to call it, so there's a Hilbert space, which is a Fock space. And there's a ground state, which I'm going to call O Minkowski. And it's chosen such that AK on O Minkowski equals 0 for all K. Can everybody see that? Can the camera see that? Okay. So that's how we quantize this scalar field in regular Minkowski space. And now we want to understand what happens when we change the spacetime a little bit. Okay? So all of this is in the realm of free quantum field theory in flat space. I haven't said anything very interesting. This is just a scalar field that obeys the wave equation. The wave equation leads us to this general solution, which I've written down right here. And if I want to quantize it by imposing the canonical quantization conditions, by making the field momentum conjugate and phi have an interesting commutation relation, then I'm led to all of this stuff. There's oscillator basis, there's energies add, so on and so forth. Okay? Now, we're not going to do the black hole yet. The black hole is too much added complications, and yeah, there's a singularity. You have to deal with the quantum fields in this space-time. It's kind of difficult. So we're not going to do the black hole right now. We're going to do a different scenario, which is very, very closely related to this one. Okay. Okay. So part one. Imagine we have an observer in Minkowski 1 plus 1, who is moving along a uniformly accelerated, who is moving with uniform acceleration. So here's a little test to see how well you learned general relativity. Okay, what is the geodesic equation for this person? No, the equation, like the differential equation. E squared x mu d tau squared. So tau is the proper time. But it's a flat space, so there's no Christoffel symbols. Exactly, there's a source term. It's definitely not a geodesic, but that doesn't mean that we can't solve it, and that doesn't mean that we can't write down an equation for it. It's just not the typical equation you try to solve when you learn GR. You have to add, this is like, F equals ma. You guys remember that equation? Newtonian physics? Okay. So, and uniform acceleration just means that there is a scalar quantity that I can compute if I dot product this A vector with itself using the Minkowski tensor. There's no event horizon. It's Minkowski. Flat space. -1, 1. We're only working in flat space. Okay. So here's our next exercise. Verify that the following for where is my 1 second. So yeah, maybe I should choose. Let's call this B, 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 B. Did I miss any B's? Okay. So verify that this satisfies this equation and find the proportionality constant between eta and tau. And xc is just another constant that you have to find. And you need to find the relation between these constants and alpha. So go ahead. By the way, this is not alpha, this is proportional. So let's just call eta equals s tau, and you have to determine s, and you have to determine all right. Let's What's the second derivative of t with respect to tau? Yeah. B squared, S squared, e to the b c over b, so this b drops out, times sinh b s. What about d squared? Tau. D squared, dx squared by d tau squared. Okay. Now what do we do? What's the next step? Plug this in. Okay. So now let's do the next step. This is just a frame independent statement, giving you a scalar. If you want the components in this frame, you've got them. You can do a boost. Okay. So, what do I want to do? Minus b squared s squared e to the 2bc yeah, sorry. That's b squared s to the 4 minus, and also the e to the bc is also going to be common, minus sinh squared of b s t tau plus cosh squared of b s tau. And I'm already predicting that I made a sign mistake. So what is this? This is minus 1. So I'm. Oh, it's plus 1. Then I didn't make a sign mistake. Very good. Cosh squared minus. That's right. Plus is equal to plus alpha squared. Okay, so all the tau dependence has dropped out. Okay, very good. So now what do we need? So we have that b s to the 4th e to the 2bc is equal to alpha squared, right? B squared. So we can solve this for s. So s to the 4th is equal to alpha squared over b squared e to the minus 2. Okay. So now we have a problem. How do we get rid of the xi dependence? Ah. Very good. Yeah. One way to do that is to, notice that this is a family of curves, and all of them satisfy the differential equation, so long as you can come up with a relationship between b xi and alpha squared, right? Because now there's no tau dependence, so you just have to fit these parameters. So one way to do it is to demand that for xi equals 0, eta is equal to tau. It's one choice. We can make some choices. So this is the choice that I'm going to make. So, eta equals to tau means S is equal to 1 for xi equals 0, right? Which means that B is equal to S is equal to 1, xi is equal to 0, B is equal to alpha. So it turns out that the correct proportionality is that matches onto this family is alpha over b, and this guy is 1 over b log b over alpha. So this whole family goes from alpha equals 1 when xi is 0, which is when b is alpha. But more generally, you can solve this and find this general relation.
So when you say demand, that for the lower side you get to 0, when you type it out, and you don't know that, so is it simplification condition or basically?
Yeah, this is a choice. These are a family of geodesics. These are a family of geodesics. So when alpha is equal to b, or when b is equal to alpha, you have xi is equal to 0, because log of 1. Okay, so what are this? What is this? What have I just described? What are these families of geodesics? So these families of geodesics, they represent different accelerating observers at different points in Minkowski space. Okay, so for example, so xi, as was mentioned in the audience, is the local coordinate of a particular observer. So an observer who is in his own coordinates sitting at xi equals 0 and accelerating uniformly will move at proper time tau. And relative to this person, different accelerating observer will be at a position b over alpha, and will the relations between their proper times is like this. So these coordinates actually fill. We can use them to fill Minkowski space. So let me draw the Penrose diagram for you. So an observer at xi equals 0 would be this trajectory right here in Minkowski. And as I move along xi, I get these trajectories. And the coordinates, if I want to, I can label the spacetime in these coordinates. The coordinates are e to the b xi. And these don't cover all of Minkowski space. So for example, for positive xi, you only cover one wedge of Minkowski space. And these coordinates are known as Rindler coordinates. Has anybody heard that word before? So Rindler coordinates are the coordinates that you get if you consider a family of accelerating observers, all at the same acceleration, but with different relative position relative to each other. So all of them have the same proper acceleration, and the Rindler coordinates do not cover all of Minkowski space. They cover a wedge. You can consider extending these coordinates to this wedge, but you'll never cover these parts of Minkowski space. Okay, so these are coordinates. They don't cover all of Minkowski space. There's a region that is behind a horizon. It's an observer dependent horizon, or it's a horizon relative to this family of observers. And the only reason that that is because we have a limitation on the speed of light, right? So the observer at c equals 0, moving at eta is equal to tau, is moving along a null trajectory, and you can't go beyond that. There's no natural accelerating observer that could violate this null trajectory. So this is why this is the limitation of these geodesics. And that object, that Rindler horizon, is for all intents and purposes very much like a black hole horizon. So the reason that it's very much like a black hole horizon is because of the equivalence principle. If you stand outside of a black hole and you're moving stationarily, you observe an event horizon, it's the same as if you were a uniformly accelerating observer and there was a part of space-time that you can't observe. It's the same rest frame physics. So there's because of the relationship between using the equivalence principle between a uniformly accelerated observer and a black hole, we're going to study now quantum field theory, the quantum field theory that we studied before, in these coordinates. Okay. It is like outside. You're outside the horizon. Yeah, but very good. But if you are outside, you're not an inertial observer, right? If you follow a geodesic, you'll fall in. So if you want to stay outside of the black hole, you're uniformly accelerated. That's the basic idea. If you want to stand at a finite distance from the black hole and not fall in, you're uniformly accelerated. And that's why these are the appropriate coordinates. Okay. So I think now's a good time for a break. And once we come back, we'll study quantum field theory in Rindler space.
These all have the same acceleration. I think it depends on like that's. I think they all have different accelerations, don't they? Because alpha depends on psi, and psi is the coordinate.
No, but if you plug this psi in there, you'll find that the b's drop out, and you'll just get alpha.
They all have the same acceleration.
Yeah. Okay. So I'm very thankful to one of the students who mentioned to me, I'm not going to name names, that actually there is a second condition, and that's how you get this solution. The second condition is that if you want to ensure that everything is following a good path for a massive particle, you have to make sure that the 4 velocity always squares to 1, minus 1. And so this is the second condition that gives you 2 conditions that allow you to solve for S and Xi. That's the thing I forgot to mention, and that is the thing that gives you this solution. Okay? All right. So as we were mentioning, so these Xi and eta coordinates parameterize a family of accelerated observers. each one of them has a different acceleration, but the observer at xi equals 0 has acceleration alpha. Okay. So now we have a set of coordinates, and there are a set of coordinates that parameterize a family of accelerated observers. And note that now these observers have a horizon. You don't fill all of Minkowski space. But nevertheless, we can still have our good old quantum field theory that we put on Minkowski space, and we can try and study it in these coordinates. Okay, so that's what we're going to do next. Okay, so the reason that we like these coordinates in particular is because you can see that up to this exponential factor in front, these coordinates are what we call conformal to Minkowski. So they are the Minkowski coordinates up to this exponential factor. But what's nice about that is that in these coordinates, the null rays are the same as in Minkowski. So the null rays are the ones that follow eta is, or xi is proportional to eta. Just like in flat space, x is linear in T, is a null ray. Here, in particular, you see d eta dx is 1, or dx d eta is 1, is a null ray. So the null rays of this spacetime are the same as the null rays in Minkowski space. And if you remember, our scalar field satisfied the wave equation for null rays. So in these coordinates, our phi field, if I just write down the action for our phi field, I would find that phi satisfies the same type of equation. And there's the same kind of general solution. So I'm going to write that down right now. So in the right Windler wedge, so remember, these coordinates, they only cover for, say, x positive, remember, they only cover this wedge. I'm going to call this the right wedge. So only cover these. And in the right wedge, we have a very similar solution as we had before. So now I'm going to write this 0 to infinity. So now I'm going to use S as my momentum instead of K, but it should not be surprising. Okay? So this should look exactly like the expression that we had before. And I know that this is not going to be caught by the camera, but let me just write down the expression that we had before, just so that we can make the analogy. Okay? So we had phi m Okay? So if you just stare at this and stare at this, you should see we have the same general solution. We have the same structure, and we have the same, you know, expectation that these A's and A daggers, B's and B daggers become creation and annihilation operators if we do impose the natural quantum field theory relations. But remember that I'm not covering the entire slice. So one last thing I want to remind you of when we do quantum field theory is that a state in quantum field theory is defined on a Cauchy slice. So we have to, they're defined in terms of the space of operators that I can act on a Cauchy slice. And because I'm working in the right Windler wedge, I'm obviously not able to excite all of the Fock space that I should have available if I'm studying quantum field theory. But no need to fret. We can just work in patches. And in the left Rindler wedge, we also have these coordinates, but we just have to make sure that we're careful about the direction of the flow of time and so on and so forth. So these coordinates also work in the left Rindler wedge, but in the left Rindler wedge, time flows this way. And that's because the d eta generator is actually a boost. And boosts move slices. They rotate slices like this in spacetime. So if eta moves positively here, it moves negatively in the left wedge. So the eta translations are actually boosts in the spacetime. Okay, but nevertheless, I can also write my quantum field theory in the left wedge, and it will look exactly the same. It's going from 0 to infinity, ds over 4 pi s, and then I will have a bs left, and now I'm going to put a dagger, e to the I s eta minus xc, sorry, c minus eta, plus bs left, e to the minus is c minus eta, plus eta goes to minus eta, and bs left goes to b minus s left. And so you see in the left, I also have a similar expansion, similar completeness, but now I've been careful to label these guys as the daggers and these guys as not the daggers, and that comes from the fact that the flow of time goes in the opposite direction, the left wedge. So these are the things that you have to be careful of if you're working in these Rindler coordinates, but it's just regular quantum field theory, free quantum field theory, nothing special. So far, I'm not setting any conditions. These are just general solutions to the wave equation, and these B's and B daggers are just quantum operators. So they're allowed. They just act on your Fock space.
Where is the horizon? Like at what coordinate?
So it's at c equals 0. Is this eta always positive? No, it's not always positive. No, it doesn't have to be. Well, it's just in this expression, so you would just take c plus eta instead of minus eta. That's what I mean. Eta can take whatever value it takes. I just mean that so these are the right movers, the others are the left movers. Okay.
So
No, no. In fact, I'm going to write just my field, my general field, or say my Minkowski field, as C? C. No. No, but it's, you see, C equals 0 is this null ray. Well, it's C equals 0, and, well, sorry, and eta equals tau is this null ray. Um, okay, I have to think about it. You might be right. But I think that, yeah, it should be, yeah, you should have t equals x in order for it to be the null ray, right? And I think t equals x, yeah, you have to, yeah, solve, indeed. Yeah, you have to, t equals x is exactly where you have to find the relation. But yeah, okay, maybe I said the wrong thing, but the null ray is t equals x. And I think it should go through c equals 0 at some eta. Okay. So now, the question is, so remember what we were doing. So we decided that we were going to study quantum field theory in these coordinates. And quantum field theory, when we talk about free quantum field theory, there's not much that we can do except talk about the states that we can excite and what is the natural vacuum, and so on and so forth. Okay, so now you imagine that you start with, say that you're a person living in Minkowski space. It's a good approximation for your life. And there are no particles around. You're kind of alone. What is your vacuum? Yeah, the no particle state. It's the thing that is annihilated by, yeah, this A, all these A's. So my vacuum, I'm going to call it the Minkowski vacuum, satisfies that AK on it equals 0 for all K. That's my vacuum. And now, say that I gave you a rocket ship and I accelerated you to constant acceleration. What would your vacuum be? It'd be different. But what state would you be in? Say that you had no particles. So the vacuum for a Minkowski quantum field theory is what is, so O Rindler. So it would be this, there's this O Rindler, and it would be annihilated by all the B's. So the B's, Bs left, right, equals 0 is the Rindler vacuum. But if you're accelerated and you start from the Minkowski state, you're not going to be in the Rindler vacuum, right? You're going to be in the Minkowski vacuum. So we have to understand how to write the Rindler vacuum in terms of the Minkowski vacuum. So we have to understand, for an accelerated observer, how they observe their state. What is, how do I write this Minkowski vacuum in terms of what I would naturally measure if I were a Rindler observer? Okay, so how do I do this? Well, one way to do that is to figure out how to relate the A's to the B's. Right? Right? You agree with that?
So just to be sure, we're moving from Minkowski to the Rindler.
No, no. We're Minkowski observers, and we're suddenly accelerated. Our state doesn't change. But the way that we measure quantum fields changes because now we have access to Rindler operators, not Minkowski operators. So we're still in the Minkowski state, and we have to understand how we express the Minkowski state in terms of the Rindler operators. Okay? They're not the same. They're absolutely not the same. That's what we're going to calculate right now.
Regarding the right Rindler, do you have to define an EL and a vacuum?
It all matters. It all matters. We'll see. Okay, so I don't have all the blackboards to work with, so I'm going to have to erase this. Is that okay? Okay, so we have that nice expression up there. Theta Minkowski is equal to theta of x minus t, phi right, theta t minus x, phi left. And we can stare at that expression up there and notice that I can extract AP, the operator AP, by taking the following Fourier transform. So I take integral from minus infinity to infinity dx e to the minus I px of phi at t equals 0, comma x. And if you do things correctly, you'll have a Fourier transform to do. And this thing should be proportional to AP. Okay? And the proportionality constant is pretty easy to work out. It's P over pi. Okay? You guys okay with that? Trust me that I did the calculation correctly? Okay. But I have two expressions for my Minkowski field. I have it in terms of the Minkowski modes. And in terms of what I just erased, I have it in terms of the Rindler modes. So I can do this calculation. I have to be very careful how I do it. There's these theta functions. But you can try to do it yourself by hand or plug it into Mathematica. But the answer is the following. Let me write it for you. It's not a very pretty answer, but it's instructive nonetheless. And I'm putting the 2 pi's and everything just to make it clear that this is super explicit. You can actually do this calculation. There's nothing hidden under the rug, okay? So you get b over p to the minus I s over b. The gamma function, 1 minus I s over b. bs left minus e to the minus ps over b. bs right dagger. And then minus b over p I s over b gamma of 1 plus I s over b bs right minus e to the minus pi s over b BS left dagger. That's a kind of a wild looking expression, but it's okay. All right, so what was the definition of the Minkowski vacuum? What does it satisfy? AK on Minkowski is equal to 0. So for AP on. So can you tell me? Can you read off what has to be true? How the Rindler modes act on the Minkowski vacuum from this expression? This whole thing equals to 0. But you can derive something simpler than just saying this whole thing is equal to 0. I'll give you a hint.
Just have to be, yeah, individual. So DSL equals
Let me write it in red. But yes, that's correct. So you now derive two conditions. You need that BSL minus e to the minus pi s over b BSR dagger on O Minkowski equals 0. And also you need BSR minus e to the minus pi s over b BSL dagger on O Minkowski equals 0 for all s. If that's true, then everything is consistent, right? Oh, it's just you're wondering why, this, why not just this single combination? That's a good question. The reason for that is that yeah, exactly. It's no, is that enough? Yeah. I think what everybody is saying is correct. It comes from the fact that as you vary p, this has to be true, and these proportionality constants change, but this is not dependent on p, so it has to be true that this individually annihilates the vacuum and this individually. No, because this is minus and this is plus. Okay. So, and you can dagger these expressions. The daggers of these expressions I'm also going to write because they're going to be useful for your next exercise. Where is my eraser? So the dagger of these expressions are that 0 Minkowski BSR dagger minus e to the minus pi s over b BS left is equal to 0, is equal to okay. So now is the question. This is the culminating point where you're going to derive that a Minkowski observer notices a temperature. So remember, you get accelerated in a spaceship. You're basically in the Minkowski vacuum. And now you ask, well, what is the thing that this accelerated observer observes? And say you're in the right wedge, right? You're moving forward in time, so you're an observer in the right wedge, and you want to calculate the expectation value of the number operator. The number of particles is the expectation value of the number operator, right? So in Minkowski space, this answer would be 0 because you're in the vacuum and there are no particles excited. But the object that you want to compute now is, and we're going to consider two different momenta because, well, you'll see very soon why. So how do I compute this? So the question is, what is the expectation value of the number operator in the Minkowski vacuum for the Rindler modes? And you have everything that you need to do this calculation. So chat with your neighbor and try to do the calculation right now. Yeah, yeah.
Okay.
For example.
So then for the acceleration observer, that'd be like at an instant where the hyperbolic is. Thank you.
It's the canonical one. Oh, L and R, they commute. Can I erase this? You guys don't need this right now? Have you guys copied this down? How are you guys doing with this calculation? No. All right, I'm going to give you guys a hint. Very good, Sasha. Let's do this slowly. So let me write the same expression. I'm just gonna write the same expression. Okay. Oops. So I've just added e to the minus pi s over b times bs left, and I've subtracted it. So I haven't changed anything, right? I'm going to do the same thing here. Right? You guys agree? I haven't changed anything in the equation, right? I've added and subtracted something, but that gives 0. So but now notice that I can use my relations. This plus this acting on this guy, 0, cancel. This plus this acting on this guy, 0, cancel. Okay? So now I have a proportionality constant, but now I have bs left, bs right dagger, bs left dagger, right? And then I should use the canonical commutation relation to commute those. So I'll get e to the minus pi s plus s prime over b. I'll get a delta function from commuting these two operators. And then I'll get and then I've related my calculation of the expectation value of the number operator in the right wedge to the calculation of the expectation value of the number operator in the left wedge. Okay? And I guess it should come as no surprise to you that I can do this calculation also in the left wedge, and I would get this expression in terms of the right wedge. So I now have two equations in two unknowns, and I can solve for it. Very easy. So the answer to this calculation, not such a bad one, is that bs right dagger, bs right prime is equal to bs left dagger, bs prime left. So you get this delta function, s minus s prime, divided by e to the 2 pi s over b minus 1. Okay, so there's an obvious divergence if s and s prime are the same. That's an ultraviolet divergence. But we regulate it by considering very close, but not so, very close creation operators. But this should be familiar to you. Can anybody name this distribution? Exactly. It's a Boltzmann distribution. And the temperature is B over 2 pi. So now you see that we have just done a calculation for an observer, a uniformly accelerating family of observers. The vacuum that they would observe is definitely not the state that you're in, because you're in the Minkowski vacuum. And therefore, an observer that measures things in these slices would notice a thermal population of particles. And the thermal population of particles is related to this B, which, as we said, was the local acceleration of an observer at x equals 0. So that is the local acceleration that you would feel at the horizon. Okay, so we have related the temperature of the quantum field theory by just doing this free quantum field theory calculation to the local acceleration. Okay, is that clear? All we did was we did free quantum field theory in Minkowski space, considered a family of accelerating observers. We asked what was the population of the quantum field in the observer's frame, and we found thermal. Okay, very good. Now, remember, the temperature of the black hole we related to R plus, right? It was 1 over 4 pi R plus. And you might ask, well, is that the local acceleration that an observer observes as of a local observer falling into the black hole? And that is indeed the case. That is the quantity that you would compute. And you would find, if you were to relate, using the equivalence principle, what the local acceleration is of such an observer, you would find that it's exactly that relation to R plus, or to the mass. So you see that this temperature is not some fantasy. It's what you would get if you just studied the rules of free quantum field theory, just weakly coupled quantum field theory, in the background of a black hole, or if you're an accelerated observer, which are related by the equivalence principle. Okay? So
for deriving things, you kind of had to define the vacuum on these kind of surfaces, right? But like if you were kind of having like the direct coordinates near the black hole, they'd only really be valid in a small set. How do you that?
well, yeah, the vacuum is always defined on a complete Cauchy slice. So you have to think about it a little bit like the maximally extended Kruskal coordinates. You would have a similar picture. There is a left wedge behind the black hole, and you can do the calculations exactly the same. And this is exactly what Hawking's calculation was to find this temperature. So to bring it full circle, when Hawking found the 1 over 4g, what he did was he did this calculation, the black hole background, did the exact same steps, and found that what t was, in terms of the local acceleration, and then that fixed the proportionality in the first law, t ds is equal to dm. Plug in that t, then you get exactly what s has to be. Yeah, but now with like having thought about it a little bit more, it's all a result of the equivalence principle. Okay, so in the last 5 minutes or so, I'm going to like rehash this idea that that the Euclidean calculation also gives the same answer. Okay, so we're gonna trying to do this holistically. We had 3 different ways of thinking about this temperature. All of them gave the same answer. Now we're going to, do that one last time. Okay? Is everybody okay with doing that for the last 5 minutes? Okay, so let me erase what I have. Okay. So remember, last time we wrote down the metric for this Euclidean black hole, right? So we drew it like this. Tau was identified, tau plus beta. And beta was 4 pi r plus, right? And we got that by considering the Schwarzschild solution very close to r is equal to r plus, and we defined a new set of coordinates. So I'm going to rewrite those coordinates again. Okay. And remember, we argued that this was a polar coordinate system. And the polar coordinate system needed to have a theta angle identified in the appropriate way. Okay? So that means that we can write it in a Cartesian coordinate system, right? So let's do that. So this is also equal to the capital X squared plus the capital Y squared plus r plus squared. And my Cartesian system is very simple to write down. Should not come as any surprise to you if I write it like this. Everybody is happy with that? Okay. So now what do we do? Well, remember that this is a Euclidean calculation. And we related the periodicity of this Euclidean calculation to the local acceleration parametrizing a family of accelerated observers. So as my final magic trick today, let's go to Lorentzian signature. So Lorentzian signature means I take t to I tau and y to it, I capital T. So so tau to it and y to it. So in my new Lorentzian coordinates, I have x is equal to rho cosh t over 2 r plus, and capital T is the rho sinh t over 2 r plus. Does this look familiar? Yeah. These are Rindler coordinates. With b is equal to 1 over 2 plus. So we've come full circle. We've come full circle. We did the quantum field theory calculation in Rindler coordinates. We found the thermal expectation value of the number operator. We went back to the Euclidean calculation of the black hole, found the Lorentzian continuation very close to the horizon, and indeed, you find that you're working in a coordinate system that's essentially Rindler. That's not an accident. That's the equivalence principle. And now, if you just think about yourself being an observer, staying outside a black hole, and you're doing quantum field theory, then you know, because of all the calculations that you've done today, that you're going to find a thermal distribution where the temperature is related to the mass of the black hole. And we'll talk more about what that means next time.